So today we are going to study both at a classical and quantum level a simple field theory. And our goal today is twofold. One is to understand this simple theory. This theory by itself is not particularly interesting, or as interesting as the theories we'll study later. It's a free theory. There's no interactions. So the scattering is a main goal of this part of the course is trivial. The initial particles are the same as the final particles, and we'll see why that's the case here. But in quantum field theory, it's very rare that we can solve any theory exactly. This is one of the few theories we can solve exactly, and when we want to study scattering for a interacting theory, generally we're going to use perturbation theory. And this is a theory we can solve exactly, and we can perturb around it. So this is a theory that we'll use as a basis for perturbation theory. And most interestingly, this theory, although it's simpler than any other theory we'll look at, does have one very interesting feature that the quantum theory does. We will examine concretely the idea that I discussed last time, that in order to specify a physical theory, we need to think or make predictions. We need to think carefully about what can be measured. So the role of measurements and what can in principle be measured will play a key role when we're understanding the quantum theory. This is something we'll come back to again and again in this course and future courses on quantum theory. Okay, so that's where we're going today. Before we specialize to the Klein-Gordon theory, which I'll define in a few minutes, I just want to make a few more brief remarks about classical field theory. Last time I made a few brief remarks about the Lagrangian and Hamiltonian formulations of classical field theory. I just want to briefly discuss Noether's theorem. Just very briefly. So in David's classical physics course, you discussed Noether's theorem already for particles. I believe next week or the week after you'll discuss it for fields. And briefly, what Noether's theorem says is that for every continuous symmetry of the system, there's a corresponding conserved current. And conserved currents also mean there's a conserved charge. We'll use this briefly in one case in this course. This is an extremely important result and something will be discussed in many other courses throughout the year, including QFT1 and QFT2, as well as a number of the electives. I'm not going to say a lot about it now. We'll come back to this in future courses, but I just want to emphasize that the derivation you saw already in David's course and the one you'll see again later in David's course is a classical result. So in this course and QFT1 and QFT2, we're going to use this classical result in a quantum theory. That's not justified. This is entirely classical. Classical result. It's often the case, and when we use it in this course in QFT1 and QFT2, it's often the case that a classical continuous symmetry leads to a quantum conserved current. That's not guaranteed. There can be quantum anomalies. Anomaly just means a quantum effect that spoils a classical symmetry. So this can occur. It won't occur in the cases we'll look at in this course, QFT1 and QFT2, but it will we will study this in detail in some of the elective courses. This is an extremely important effect. There's lots of interesting physics there. We won't touch it for now, but just I want you to be aware that we're doing something that's not justified in these first courses. We're using a classical result to make a statement about the quantum theory. Okay. So our focus is going to be on the Klein-Gordon theory. Okay. And Klein-Gordon theory is defined with the following Lagrangian. So it has a term that involves derivatives of the field. And it also has a term that's m squared phi squared. So here phi is a real scalar field. We'll look at the complex version of this theory later, but for now we'll focus on the real version of this theory. M here is the mass parameter. Okay. So the reason this theory is so simple is that if we look at the equation of motion, or Euler-Lagrange equations, starting from this Lagrangian, what we get is d mu plus m squared phi equals 0. This is the equation of motion. And this is linear in the field.
Hey, Dan.
Yes, Petra?
I feel like I always ask this question in previous courses, and I always forget the answer. But like, why in QFT is our mass term always like squared when in any sort of classical theory m is just not squared?
One answer to that is dimensional analysis. So if we're working in 4 space-time dimensions, the mass dimension of S is 0. That's true in any space-time dimension. But the Lagrangian, S is 4 dimensions, is the integral of the Lagrangian. So x and t have dimension -1, so the Lagrangian has to have mass dimension 4 in 4 space-time dimensions. And the field, if we look at this term, the d squared phi squared term has mass dimension of, this is a derivative, so it's 1 over time or space. So this has dimension 1. So we have 2, there's 2 derivatives plus 2 times the mass dimension of phi. And so that tells us 4 is 2 plus 2 phi, so phi is 1.
Is there any more intuitive explanation? Because like, although this is true and this works out, can we like, is there any way to understand why it may physically be the case?
Yes, we'll look at, based on what we've seen so far, this is the simplest answer I can give. We'll see. Yeah, we're going to discuss the interpretation of this parameter later in the course. Not today, but we'll see a few other ways to look at it. But based on what we've seen so far, this is the simplest answer I can give. Yes.
What confuses me a lot is we are working with +1 and 3 minus metric.
Yes.
So the final equation of motion should be something like E squared is equal to P squared plus M squared. So
yes.
If we like write dou T square as like E squared, then this is E square minus P square plus M square is 0. So shouldn't there be a minus M square? This thing confuses me.
Okay, so if we expand this out, so these are, we can also write this d mu as d e nu eta mu nu. So this is e t squared because eta 0, 0 is 1. Eta I is -1, so this gives us a minus.
So is it not like e square minus p square plus m square? So
We'll see that in a minute. We're going to solve this equation and find the solution. It's essentially there's if we look at the mode of phi that has momentum k, that there's an e to the I ikx. There's an I there, Fourier expansion. Okay. So this is our equation of motion. It's linear in phi, which means we can solve it exactly. And we'll do that because the explicit solution of this equation is going to be useful in understanding quantum theory. Okay. And one way to solve this equation is to take a three-dimensional Fourier transform. You could also do a four-dimensional Fourier transform. I think the three-dimensional is a little bit easier, so that's what we'll do. And we can write phi of x as an integral e3 k phi cubed e pi a dot x times, I'll write this as phi of x t times the Fourier transform k and t. And so if I plug this Fourier expansion equation to motion, what I get is phi tilde double dot plus k squared plus m squared tilde is 0. And the sign switches because of the i's. Okay, so this is an equation we can solve basically by inspection. We've got the second derivative is some constant times function. So the solution to that is phi tilde k t is some constant we call a of k, e to the minus I k dot x. That should be 4 vectors. B of, sorry. Yeah, this should just be e to the ek, e, b of k, e to the I, ek. That's our solution, where ek is just the energy of a relativistic particle. Okay. And we haven't yet imposed that the field is real. So we want the field to be real. We should have that phi x t equal to phi star x t. And that implies that that we rewrite the Fourier expansion. We should have integral d3k 2 pi cubed to the minus e to the plus I k x I tilde is same thing but conjugated. And so if I conjugate phi tilde, I switch A and B, and the coefficient that then tells us that one more step. So here we have e to the ikx, and here we have e to the minus ikx. So we can't directly compare the coefficients. We want to change this function in order so we can compare the coefficients and make a statement about the relationship between A and B. We can do that by noticing that if we do a change of variables, we do a change of variables, k goes to minus k. We change k to minus k here and here. In the measure, we get 3 minus signs. We also get 3 minus signs from switching the order of integration. So the overall, there's no minus sign, an even number of minus signs. Conjugated. So now we can compare the coefficients of e to the ikx between this phi star of minus k and phi of k. Gotcha.
Questions. First of all, I think I missed when you said, how come we're assuming the field of phi to be real?
That's an assumption. We're defining the theory by saying that this is the Lagrangian and that it's a real scalar field.
Oh, okay. Okay. And then also, sorry, where was the fourth minus sign? Three were in the measure. And
three were from the measure. So when we do this, dk goes to minus dk in each of the 3 directions. This integral is an integral from minus infinity to infinity in each of the directions. And those limits will switch. We can switch them back.
Okay. Got you. Thank you.
And
Is it a good assumption to assume that the scalar field is real?
It's just the assumption.
Why is it good?
So that we'll see later that whether the field is real or complex corresponds to whether it's charged or neutral. So this is an example of a neutral particle that has no spin. That's what we're going to find when we quantize this theory. If we wanted to have a charged particle with no spin, we would want to make this a complex. And so this, we now, by comparing this last expression, this first expression, we see that phi tilde of k t has to be equal to phi tilde star of minus k. Or, in other words, e of minus k is a star of k. Or I can put the minus sign on either side. B is A star. By comparing the coefficients of e to the I k t and e to the minus I. Okay, so what we get is that phi of x t then is an integral d3k 2 pi cubed of a of k e to the minus I e k t plus I k dot x, and our other term is a star of minus k e to the plus I e k t plus I k dot x. And so this term, this first term, the coefficient of a k, you've got a nice Lorentz invariant, or manifestly a Lorentz invariant combination of t and x. This relative minus sign between the time component and the x component, we can write this easily as the product of two 4 vectors. Write this as e to the minus I k dot x, where we're defining k0 ek. This term doesn't look so nice. We have a relative plus sign, but we can do the same thing we did before. Change of variables k goes to minus k to flip the sign here. And after we do a k to minus k, this term becomes a star k e to the plus I k dot x. These are 4 vectors. Okay. So, yes.
So I'm a bit okay. I follow this derivation, but I'm wondering like what's preventing us from just saying that because we want phi tilde to be equal to its conjugate, then AK has to be equal to BK conjugate. No, the conjugate of AK has to be equal to, like, what's preventing us from just directly using that?
Directly.
Because the result.
Well, we know that phi and phi star are conjugates. What we showed is basically that implies a relationship between phi tilde and phi tilde star, but it's not just that phi tilde is equal to phi tilde star. There's a minus sign in the argument.
I see.
This was our assumption, so that's why I started there.
Compare the coefficients, you would also get b star minus k is equal to ak. I know there shouldn't be any new information in that.
Mm-hmm.
How I can show that? How can I show that?
You could take the conjugate of that equation and substitute k with minus k. You'd end up with that equation.
Makes sense.
Okay, so this is not quite the final form we're going to use, and that's because this measure, well, it's an integral d3k, and it's going to be useful for us to write this in terms of a more Lorentz invariant measure. D4k is manifestly Lorentz invariant. D3k is not Lorentz invariant. So we're going to redefine some things so we can get a Lorentz invariant measure here. And that will have an advantage when, in the quantum theory, that our operators will have much nicer Lorentz invariant properties, and our amplitudes will also be Lorentz invariant without lots of extra factors. So let's play around with the measure to write this in a nicer form. So we want to write our measure D3k as a measure D4k. Or we can try to, it'll be easier to try to work backwards. Start with this and see how we can write it in terms of D3k. Let's do that. So let's start with the D4k. And we want to relate it to a D3k. So the natural thing to do here, if we want to get rid of an integration, is to throw in a Dirac delta. And if we want to maintain Lorentz invariance, it should depend on some Lorentz invariant quantities. So the only thing we can really write down is k squared or m. So we put this delta in, we've reduced our D4k to a D3k. But this is not quite just equal to D3k. And that's because a delta of a function of x is equal to a sum over the roots of xi of a delta of x minus xi over f prime xi. And so this, if this familiar formula isn't familiar to you, using it again and again. I have a short video on distributions. This Dirac delta is known as a distribution. It's not quite a function. My very brief summary is that distributions behave just like functions, more or less, if you keep them under integrals. They behave weirdly if you take them out of integrals. There's more details in that video, even more details in the appendix of the lecture notes if you're interested in seeing some more mathematical rigor. But this formula, one way to motivate it is just if you have a delta inside of an integral, you can do a change of variables and you get this extra factor. And so in this case, if we put in this delta of k squared minus m squared, this argument, k squared minus m squared, has two roots. It's one root where ek, where k0 is equal to ek, is the one we want, but it also has a root where k0 is minus ek. And we don't want that solution. We want k0, our particle, to have positive energy, not negative energy. So we can get rid of that solution by throwing in a step function. This is a step function. And this doesn't look Lorentz invariant. It depends just on k0. But at least if we restrict to Lorentz transformations that are continuously connected to the identity, those won't change the direction of time or the sign of k0. And so this measure is manifestly Lorentz invariant. We can write it in terms of we can use essentially this delta to do the k0 integral and leave us with d3k over 2 pi cubed. But we also get a factor of 1 over 2 ek from this formula. This is not a delta of k0, it's a delta of function of k0. So this is our Lorentz invariant measure. And in terms of this Lorentz invariant measure, we can write our final form for solution to the Klein-Gordon equation. This is a formula we'll be using over and over again in this course. So we want to write like this. And I'm going to redefine the mode functions A by defining A of k, big A of k to be small a of k over 2ek. So just pull out the extra factor that we were missing before. And this gives us A of k e to the minus I k dot x plus A star k e to the plus I k dot x. This is our final result. And one comment on this. So here, so this should be 3 vector x. We're integrating over just 3 components of k. In these exponents, we have k dot x. So what does this mean? What do I mean by 4 vector k? We're only integrating over 3 components of x. So here we're integrating over d3 3k, and here I've written intentionally a 4 vector k. How is k0 defined? ek. Yes. So this I'll often leave this out, but implicitly this equation means that k0 is ek. It's important that these are 4 vectors here, but we're only doing a 3-dimensional integral in momentum space. Yes.
I have a question about fixing the Lorentz symmetry. So the last step function there fixes from the notes here. Is it like orthochronous transformation? Is that the like?
Yes, orthochronous means the Lorentz transformations that don't change the direction of time.
So I'm wondering, because it seems to me in classical physics, or like in the Lagrangians we had before, they also respect Lorentz transformation that even reverses time, right?
Yes.
So why do we enforce this arrow of time here?
Well, a simple, not a very deep answer, but a simple answer is if we don't, we have an extra term here that has k not equal to minus ek, which we don't want to agree with what we have here. The bottom equation here is also evaluated with k not equals ek. If we want this equation to rewrite the measure in a way that we impose that constraint that we have, we need to put that step function in there. There's lots of interesting things to say about time reversal, which Gang will tell you about in QFT1, but that's a rather big detour from where we're going in this course. Okay. So we're finished with classical theory. That's all we need, basically, for classical theory. Now let's quantize the theory. Okay, so we're going to use canonical quantization. which is a very direct generalization of the quantization procedure you're all familiar with from non-relativistic quantum mechanics. So let's just briefly review that. So our procedure for defining a quantum field theory by a canonical quantization is first to choose a Lagrangian. We probably want this to be Lorentz invariant and local. For now, we'll choose L is the Klein-Gordon project. We could make other choices, and in this course, we'll basically consider the Klein-Gordon theory or the complex Klein-Gordon theory. But the same procedure will work for other field theories that you'll study in. Okay. Our second step, second thing we need to do is compute the conjugate momentum, Hamiltonian. So that in this case, the conjugate momentum is the derivative of the Klein-Gordon Lagrangian with respect to phi dot. And what is that? This derivative equal to? Phi dot, yes. Phi dot. Thank you. So the only terms that depend on phi dot in our Lagrangian are the terms from the 0, term from that derivative there. And that's the phi dot dependent term is a half phi dot squared. Take a derivative we just. And our Hamiltonian, we won't need quite yet, but we can compute this using the usual formula. It's phi dot I minus L. And this will turn out to be integral 3x of a half I squared plus a half gradient squared plus a half m squared phi squared. And we can interpret this by saying the Hamiltonian is this is a kinetic energy term, a gradient energy term. There's energy associated with having a field that varies in space as well as in time, and a potential term, mass term. We can think of the, sometimes it's useful to think of the gradient term as a potential term as well. Okay. Next thing we need to do is promote our classical.
That before moving on.
Yes.
I didn't understand how did you write the inequalities and results on what we expect from energy, or we calculated
We calculated from here. Sorry. The Hamiltonian density. This formula is a little bit. Hamiltonian density should be this. Then the Hamiltonian, which is the integral of the Hamiltonian density. Thank you for catching that. Sorry about that. Yes.
Sorry, this is going back to the field solution.
Yes.
You said that measure is only Lorentz invariant as long as we consider transformations that are kind of identity.
Mm-hmm.
But we can have Lorentz transformations that are not connected to items,
Yes.
the field should still be invariant under those transformations, but the measure won't be.
That's right. Yes. You absolutely can consider transformations that are not continuously connected to the identity. Parity transformations, time reversal transformations, or card conjugation. And so there are interesting field theories, quantum field theories, that respect the local part of the Lorentz group, the part that's continuously connected to the identity, but they don't respect these discrete transformations, the generators of the parts that are not connected. Some theories, like this theory, will respect those, but there are others that they won't, and you'll discuss those in quantum field theory 1. There's very interesting physics, those transformations. We won't have time to discuss. So our next step is to promote phi and pi operators. And we do this by imposing commutation relations. It's exactly the same way you done in non-relativistic quantum mechanics. In non-relativistic quantum mechanics, what you'll impose is that you have some set of generalized coordinates and their conjugate momenta. Commutation relations you'll impose are that the commutator of QA PB is I h bar, setting h bar to 1, if A is equal to B or 0 otherwise. I delta AB and all of the Q's and all of the P's commute themselves. And we can just do an immediate generalization of this for get a quantum field theory. So the field, like the generalized coordinates. So we're going to impose a commutation relation that phi of x b with pi of y sorry, I wanted to start with the Schrodinger picture. Write it like this. Phi of x with pi of y is I times a delta. X is like the label we had before, A, and Y is like B. The difference is that A and B were discrete, X and Y are continuous, so we need to replace the Kronecker delta with the Dirac delta. And these are Schrodinger picture operators. They're time independent. And everything else commutes. So just analog of these equations, we have that phi of x, phi of y, phi of x with phi of y. These are 0. This is the key step in the quantization procedure. Take our classical objects, promote them to operators. If we do that, we also need to promote something on the right-hand side of this equation, operators. So after we quantize phi, we're going to quantize our mode functions, a of k and a star of k.
When we say that we promote the fields or to operators, in quantum mechanics we know that those operators are operators that act in the Hilbert space of states
Yes.
of our physical system. If these are operators, in which space of states are they acting?
We'll discuss that. Very good question. I'll get to that, but let me just cover that.
I'm a bit confused what you mean by like Schrodinger for the phi of x and the phi of y.
Mhm.
How do you mean that these no longer depend on time? Because phi of x, as in phi, the field is usually x and t dependent.
Okay, so the Schrodinger picture and Heisenberg picture operators agree at a fixed time. I can choose that fixed time to be 0. So if I just set t equal to 0, or take our Heisenberg picture operators and set t equal to 0, that's our Schrodinger picture operators. That's one thing. We'll discuss the Heisenberg picture operators a bit later, but they behave more or less like you'd expect. Instead of just having phi be a function of x, it'd be a function of x and t. The important thing is that this commutation relation is at equal times. This is at, you can think of that, this is at equal times. Here it's at t, you can think about it as equals 0. At unequal times, the commutation relations won't be quite as clean as these.
This is kind of confusing me because we started by saying that phi is a function of x and t, and now we're saying we're looking at the Schrodinger picture in which the operators do not depend on time. Did we use the time dependence anywhere in the calculations? Because we had minus EKT there.
Okay. I was planning to discuss the Schrodinger picture first and then the Heisenberg, but I can just write down the Heisenberg picture version of these equations. And the Heisenberg.
No, I'm fine with the Schrodinger picture as well, but I'm just saying that we defined our phi to be a function of t as well, but here we're saying we're not, because we're working with the Schrodinger picture. Then why didn't we say that phi is not a function of t from the get-go?
Well, the solution to the Klein-Gordon equation depends on time. Our solution to that should depend on time as well.
But you're not going to use that result here?
So in the Schrodinger picture, we just need this result evaluated at t equals 0. For the Heisenberg picture, we need it for all time. But in both cases, we're using this. So if we promote the field to an operator, we also need to promote something on the right-hand side to operators. And in this case, the natural thing to do is to promote the mode functions, a and a star, to operators. So a becomes an operator, which I'll also call a sub k. This is an annihilation operator. I haven't justified that yet, but you'll see that this operator destroys particles. And a star of k will become a creation operator that creates particles. These commutation relations imply commutation relations for these operators. And you'll derive those in a quiz. The result is AK, a dagger E is 2 pi cubed 2ek delta p minus k. And the rest commute. Yes, Stoic?
When we promote the A star coefficient to
Mhm.
A dagger,
Yes.
why A dagger and not just A star as an operator? The conjugate of the first operator, that would be.
It's just a notation at this point. The motivation for the notation is that for other types of fields, these will no longer be functions, but they'll be functions with multi-component functions. Or you can think about it like vectors. So that the dagger will be important in other contexts. Here we're just using it for notational consistency. Okay, so once we've promoted the fields and the mode functions to operators, we almost have a quantum field theory. One last subtlety, which I'll say a little bit about after break. Good time to break for 5 minutes. If you want to break, at least, yes. I can continue, but please break. Okay. Yes, go ahead. Yes.
Lorentz invariance of the Lagrangian.
Yes.
And we were making sure that the Lagrangian density was Lorentz invariant.
Yes.
My problem is the measure of like the integral over d cubed x. Is that going to be Lorentz invariant? Or is that overall Lagrangian?
No, the Lagrangian is not Lorentz invariant, but the action is.
Okay, so like the Lagrangian density and the action are Lorentz invariant.
Yes.
Not the actual, like.
That's correct. Yes.
But this makes sense here, yeah.
Yes.
So I think in here our commutation relation has a 2 pi cube in front of it.
Yes.
I've seen other factors of it's like a normalization thing. Like
Yes.
it seems to me that we just got things the 2 pi's from the what's it called Fourier transformation. Is it just so?
It's
other factors like what's like.
This E?
No, like the 2
E?
Or the 2E, or I've seen like square root of 2E's and stuff.
Yes. So the advantage of this normalization is that our operators will create Lorentz covariant states. And our amplitudes will be Lorentz invariant. If you choose other normalizations, the Lorentz transformation properties of the states created by these operators are not nice. So.
I guess my question is more like, how do we choose our normalization? Because it seems to me that every step we're just using, like the 2 pi just comes from Fourier transformation. So, like, where is the freedom to choose?
The 2 pi is 2 pi.
Or like the
right.
and stuff.
The choice really is how do we define the mode functions? I could have promoted the big A's to operators, or I could put a different factor here. That's the freedom.
Oh, okay.
This choice is particularly nice. Well, the commutation relations and the measure are not nice, but everything else is nice.
That's fine. Okay.
Yes.
How you got the roots of k squared minus m squared?
The roots. Okay, yes. So get the roots. I'm writing k squared as k naught squared minus k squared. Or rather, I'm writing k squared minus m squared as this minus m squared, which is k naught squared minus ek squared. And so the roots of this as a function of k naught squared are plus or minus ek.
Thank you. I think I got confused with the 4 vector, 3 vector lambda.
Yes, Ellie?
About how you got from that phi to the other phi. I understood all of this completely, but when you change from k to minus k, the e to the power of pi kx's are not here.
Okay, so well, ek is equal to e minus k.
Okay.
Because ek is okay. So if I take in this term, if I take k to minus k, the measure doesn't change. A star k goes to a star minus k goes to a star k. This term doesn't change, but I do get a minus sign here.
Yeah.
So I get a overall the term is a star k e to the plus ik.
So, but when you wrote it down there, you said it's a star e to the power of plus ikx.
It's the same plus it is here.
No, because up there it should have been e to the power of minus ikx, because you had plus ikx and then you changed the sign of k to minus k.
So remember, we're using the mostly negative signature.
Okay.
So the time component is positive. Spatial components are negative. So here I've got the ekt, and after the change, it's minus k dot x. That's why this is a plus. K dot x is ek t minus k dot x. Yes.
E Dirac delta is Lorentz invariant or E Dirac delta?
E is not Lorentz invariant. E is an energy. It transforms like an energy. The product ek times the delta. Yes.
So when we take commutation of phi and pi, there is no ek, so that commutation is not Lorentz invariant.
This is Lorentz invariant. Both phi and pi are Lorentz scalars. They don't transform. Oh, sorry, that's not true. No, phi is pi does have has a time derivative, so it transforms not trivially. So, sorry, I misspoke there. So that, and you can see manifestly on this side, that's not Lorentz invariant. Reductor. When m is 0, there's no mass.
It seems like major divergence when k goes to 0.
Yeah. Yes, there are. So there are divergences when m equals 0. In this measure, when k equals 0 and m equals 0, yes, there are diverges.
Still, the integration is really fine.
There are subtleties in that case. So again, one way to resolve them is to think about physically what you can measure, and if you there are extra questions that don't have well-defined answers in the m equals 0 case because there are subtleties about very low energy massless particles. Those are very hard to observe, and if they're sufficiently low energy, they can't be observed. You need to account for what you can measure in order to ask a well-defined question. Yes.
Just wondering whether these commutation relations are consistent with the picture Hamiltonian of that form should generate stand translation activities.
Yes, it does. Okay. Okay, let's resume where we left off. One other comment I'd like to make that we'll use in a few minutes is that we can re-express the Hamiltonian in terms of these creation and annihilation operators. This result will be useful in a few minutes. We're going to use it. Again, I'm not going to derive it. It's on the quiz. You can derive it. And in terms of the ladder operators, the Hamiltonian is There are two terms, one with an AK dagger and one with an AK dagger. These terms are the same except for the order. This follows just from plugging this equation into the Hamiltonian. Do that here. And, oh, sorry, there should be a half. D3, yeah, D3. Okay, and there's one last point in the quantization procedure, and that's that we need to impose an ordering condition. And one way to think about why we need to do this is that in going from the classical theory to the quantum theory, there's an ambiguity. And the ambiguity comes from the fact that in the classical theory, everything commutes. In the quantum theory, it doesn't. So I take the classical Lagrangian and add to it phi dot minus phi dot phi. I've added 0. This is 0 in the classical theory. And non-zero in the quantum theory. And what theory I'll end up with will depend on what choice of coefficient I put here. So there's an ambiguity in going from the classical theory to the quantum theory. And we can, so one way to think about this is we need to impose an ordering for the operators that appear in the various expressions in our quantum theory. This is what we get if we just take the Hamiltonian, plug in that expression we derive for the classical field. And this is the Hamiltonian, but we could get a different Hamiltonian if we added some commutators of phi and phi dot, or phi and pi. So there are some choices of ordering that are more natural and easier to use, and we'll see that there's a nice choice for an ordering prescription. We'll see in a few minutes.
The expression for Hamiltonian, the EKs cancel.
They do, yes. These cancel. I'm just leaving it so that this is our Lorentz invariant measure. Okay, so coming back to your question about the state space and what are these operators acting on, let's discuss what are the states in this theory. So we'll start by defining a simplest state in the theory, and we'll build up all of the other states by acting with our operators on this state. The simplest state for this theory, the vacuum state, I'll denote by 0. And this vacuum state has two properties. One is it's a state with no particles. So we act with an annihilation operator on the vacuum state. There's no particles there. We can't remove a particle. There's no particles to begin with. So the annihilation operator acting in the vacuum is 0 for all k. That's almost enough to define the vacuum. We're going to make one other assumption, which is that it's normalized, unit normalized. So that is a very simple state. In a moment, we'll construct other states by acting with creation operators on the vacuum. And in general, our state space is going to be spanned by the states with n particles with definite momentum.
Maybe this is a basic question, but how do we know that such a state exists as like an eigenstate of the annihilation operator? Like if you take any operator on space, it's not necessarily going to have a solution like this. Is there a way we can force this to be true, or?
So showing that this is true, that this exists in general in a quantum field theory is a difficult question, but if you start with a classical theory that has a unique ground state, it's often the case that you end up with a quantum theory that has a unique ground state. The classical theory has a unique ground state where phi is 0 everywhere for all time. We can think about the existence, for our purposes, we'll think about this, the existence of this state as an extra assumption.
Is this set at a particular time, or is it?
No, this is for all time. So we're also going to assume that, so 0 is Poincare invariant. If you like, we can just take these as assumptions. The reasonable physical assumptions, but
continuing on this question, so the Hamiltonian should be bounded below.
That's right.
Put that assumption there.
Yes. Yeah, the Hamiltonian should be bounded below. The particular Hamiltonian we have is bounded below. So this is the simplest state we have in the theory, and let's examine the properties of the state. So one question we can ask is, what is the energy of the state? In other words, what's the ground state energy? And we can find that by acting with a Hamiltonian on the vacuum. And if it's an energy eigenstate, this eigenvalue will give us the ground state energy.
Sorry, Dan?
Yes.
What do you mean by the vacuum is Poincare invariant?
This state is invariant under translations, space-time translations, as well as Lorentz transformations.
Yes, but is that an assumption you're making? Or?
Yes, we're making this assumption.
Thank you.
Okay, so let's compute the ground state energy. If we take our Hamiltonian and act with it on 0, get is this, and we have an extra EK. And then we have two terms here. AK dagger, you can act with on the ground state, and this other term. And acting with the second term on the ground state is easier. What do we get if we act with AK dagger ground state? 0. So that term vanishes by this condition that the ground state is annihilated by the annihilation. So we're just left with AK dagger, and 0. And to make further progress, basically have one tool at our disposal, which is the commutation relations. So we can use the commutation relations to write AK dagger in terms of AK dagger AKA and plus the commutator. And what we get is integral d3k ek half and 0. The commutator gives us something that exactly cancels out the denominator here. and the term where the operator's in the other order vanishes when it acts on them. And so this, sorry, I'm missing a factor. There should also be a delta of 0. And so if we look at this expression, this looks horribly divergent. It's got a delta of 0, which is unclear if that's even defined. It also has an integral d3k of something that grows for large k, like k. So this is horribly divergent. So something went wrong here, and well, what went wrong is that ground state energy is not something we can, at least in non-gravitational physics, not something that's observable. So we didn't have asking a question about something that's not observable, and not guaranteed to get a finite answer. It's useful to understand where the origin of this infinity a little bit more, though. And we can modify the question we're asking a little bit to get asked about something that's observable. So this is not observable. So we're not overly concerned yet. It's not observable, and it's not finite. Okay, so where did that infinity come from? There's a delta of 0 there, which we can think about in the following way. If we write delta of 0, we can write this as, so delta is related to the Fourier transform of the identity. And we can relate this to the Fourier transform of the identity in the following way. Write it as a limit, L goes to infinity, of integral from minus L over 2 to L over 2, d3x e to the I of 0 times x. So delta evaluated at 0. If I take the limit L goes to infinity, this is just an integral over just a Fourier transform of the identity. And I'm putting in this limit to what see that we can think about the expression on the right-hand side as well, this factor is just 1. And over here, we've got an integral d3k of, we put space in a box, make the box very big. This is just the volume of space. So one way of thinking about why we got infinity is we're looking at a quantum field theory in Minkowski space. Minkowski space has has infinite volume. Minkowski space. So of course the energy of the ground state is going to be 0 in infinite space unless the energy density is 0. You can write E naught as rho naught times V. And this is going to be infinite, and if the volume is infinite unless rho is 0. What we found is that rho naught, the energy density, which is integral e3k 2 pi cubed half ek, is also infinite. So there's two divergences here. This first one is related to long distance physics or low energy physics. This is often called a IR divergence. And the second one is a high energy divergence. This integral diverges. For large k, this grows like k. Will be 3k of k diverges with a large momentum or large energy divergence. Or violent. Yeah. So this ground state energy diverges for two reasons. Not so important because it's not something we can measure directly. In fact, we can eliminate this divergence by choosing an ordering prescription.
Say we assumed we're in like a bounded space-time.
Yes.
So would that only fix the infrared divergence? That wouldn't fix the UV divergence?
Exactly, Batcha, yes.
Is there a way to do something like choose something to fix the UV divergence in the same manner as like choosing a space-time?
Well, so this is not observable yet. But we're going to define something closely related to this that we can observe in just a minute. But yes, there are procedures we can do to modify our theory to eliminate or better understand. And we'll do that. And we can get rid of this problem by normal ordering. Define a normal ordered Hamiltonian, which is roll d3k, 2 pi cubed, 2 ek of ek ak dagger ak. So this is different from the Hamiltonian we had before. I just switched the order of some operators. So these dots are normal ordering. And what they mean is that the normal ordering of some set of operators just means by hand, without using the commutation relations, push all of the creation operators to the left and annihilation operators to the right. And so the normal ordered Hamiltonian, back in the ground state, gives 0. So we define things with the normal ordered Hamiltonian, the ground state energy. We just subtracted off the divergent ground state energy, which is unobservable anyways, by doing something like this, explaining this ambiguity.
Why would we allow to do this? Like it's just like saying that going back to the non-quantizing version of like Hamiltonian, because we're practically saying here that A dagger and A they commute with each other. So
we're not. We're using this to define our quantum theory. Before,
it's like completely changing the Hamiltonian and
it's not changing any observables. We couldn't observe this. This divergent ground state energy. You can only observe energy differences. So in a sense, this is like choosing a reference frame, a more convenient one, instead of choosing a reference frame at minus infinity, or origin at minus infinity, or plus infinity, we're shifting things around.
if you want, what if you like apply this normal ordered Hamiltonian on other states, not like vacuum state? Something should change here, like.
Yes. So other states.
Quantization was putting this condition there between A and A dagger that they don't commute with each other.
Other states. Sorry. Go ahead.
Go on.
The energy of other states will all shift by an infinite constant. The difference in energy between any two states is the same with the original Hamiltonian or the normal. And that's what we can observe. The difference in it.
Sorry, I don't think I quite understand this normal ordering by being able to push the annihilation operators to the right and the creation operators to the left, we're saying that this row knot is 0, like we're defining it, because the difference between like AK, A dagger P, and AP dagger AK is going to be the delta 0, so we're just saying like ignore that term.
Yes. Yep, it's not observable. We don't need to care about it. Okay. We can discuss this more in tutorial if you like. I want to cover one more thing before end of class today. So how can we observe something like the ground state energy?
Going back to the Hamiltonian acting on the vacuum state, we had some expression like a dagger acting on the vacuum state, and then we used the commutation relation to get a delta, and then we wrote the vacuum state again. But the creation operator, the annihilation operator acting on the vacuum state does not give the vacuum state, it gives 0, the number. So that whole integral should be something like 0, no?
When we use the normal ordered Hamiltonian, yes, we just get 0.
No. Even if we don't use the other ordering, the action of the annihilation operator on the vacuum state is
0. Yes.
Two terms, one term with the annihilation, one term with the constant delta.
Oh yeah. Oh, sorry. Yeah, thanks.
Okay, so how can we measure something related to the energy of the vacuum? One setup we can do is we can try to modify vacuum energy by putting some plates that change which modes are allowed for our field. So explicitly, we're going to imagine there are 2 parallel plates. And we're going to work in one spatial dimension plus time with a massless field. And we're also going to make space periodic to avoid the infrared divergence we had before. So plate one, let's say, is a distance of A away from plate 2, but space is periodic. So this distance here is L. So plate 1 is also a distance of L minus A away from plate 2. We're putting these plates to impose boundary conditions on our field, which will change the modes that are allowed in our expansion. So in Minkowski space, our scalar field had any k was allowed. We put these plates that impose boundary conditions that fix the plates fix. I'll assume the plates fix phi to be 0 at those locations. So that will restrict which modes are allowed. So we're changing. So by moving the plates, then we're changing which modes contribute to the ground state energy, and we can get force. There's a position-dependent energy for the location of plate. So if m equals 0, then Ek is just k, and we're in one dimension. So we can also think of this as the frequency of the mode. So the energy inside a box of R, this is the energy inside a box of size R. We've got 2 boxes here, one of size A, one size L minus A. So if we want to find the total ground state energy, we'll just add up this energy for R equals A plus R equals L minus A. This will just be the sum over the allowed modes, which are indexed by an integer n, of the energy of the modes, which is just 1/2 omega n. And the allowed modes are omega n, where this is n pi over L. So our ground state energy, E naught, depend on A, is E of A plus E of L minus A, which, using this formula, is 1 over, or pi over 2L, sorry, pi over 2 L, 1 over L minus A, plus 1 over A minus the sum, equals 0 to infinity. So this clearly diverges. Sum of the positive integers. This diverges. That's not a problem. That's not what we were trying to compute. What we're trying to compute is the force on the plate. We want to compute how the force changes as we change A. The force is minus E naught EA, which is pi over 2 1 over A squared minus 1 over L minus A squared, sum of n equals 0 to infinity. Does this diverge? Yes. Yeah. So this diverges. So this is a real problem. This is no problem. This is fine. This is not. So something really has gone wrong here. This force is definitely something we can predict. Put two plates in a laboratory, we would notice if there was an infinite force, they go flying off or smash together. That would be a very obvious thing that we couldn't possibly miss. We don't see that. This prediction is wrong. So we've done something wrong here. We've made a mistake. This calculation is wrong. And what we've done wrong here is we haven't thought physically about this problem. There is no plates we can make in a laboratory that could impose this condition for arbitrarily high energy modes, arbitrarily high frequency modes. A mode of the field that has a very high frequency will have a very short wavelength. Any mode we can make, any plate we can make in the laboratory will be made of atoms. There'll be some spacing between the atoms, and sufficiently high frequency, the waves will just pass through the plates. So high frequency modes are unaffected by the plates. And we have to account for that. We can't get a physical prediction if we don't take into account all the physics. And one way we can account for that is to say that only modes with omega less than some cutoff, or pi times some cutoff, are affected by the motion of the plates. Only these ones are affected. And that changes our expression for the ground state energy and the force. So the modes that are have a dependence on the position of the plates, those are the only ones that will contribute to the force. And the energy of those modes will just be from n equals 0 up to some n max, 1/2 omega n. And n max will be the floor of yes, floor of lambda a. Or lambda r. R. So we shouldn't include all the modes. High frequency modes are unaffected. We really not include in our calculation of the force those modes that pass through the plates. And we can rewrite this after some algebra. I won't do here. And find that the ground state energy is pi over 4 L lambda squared. And it's pi over 4 AX. AX 1 minus X. X is the fractional part of lambda A. And so what's the, we look at the ground state energy versus A. What it will do as we vary A, this term here will oscillate. It reach a maximum value of pi L lambda squared over 4, and it will oscillate. The oscillations will get very large, and we can average over them. And the lambda goes to infinity limit. You do that. What we find is that, well, the ground state energy diverges in the lambda that goes to infinity limit. The force won't depend on this term. It will only depend on this term, which doesn't go to infinity as lambda goes to infinity. What we'll find is that the force is minus over 24 a squared. So this is finite and observable, even in the limit lambda goes to infinity. And so this is something we measured in the lab. Go ahead.
Going back to the energy inside the box.
Yes.
You're summing over all the modes n, and you're also at the same time calling it the ground state energy. So in quantum mechanics, for example, we don't get ground state divergences because the ground state energy only depends on n equals 0 mode.
So this is the energy associated with the lowest energy configuration of the field. in a rough sense. We could add extra excitations of the field beyond the state that has this energy. But this is the lowest. This formula is a direct analog of the formula we wrote for the ground state energy before, which I think I covered up, where we were integrating over all the modes of 1/2 of the energy. So that's by that analogy, it's the same thing we were looking at before. Okay, so what we found, I've skipped a few steps that are of algebra, going from here to here. That's some algebra, and also taking the derivative to get this expression. But what we've seen is that when we compute an observable, we take account all the physics, we get a finite observable answer. We had to regulate our theory in order to get here. By regulate, I mean introduce these cutoffs. Introduce 2 cutoffs here. We introduced a UV cutoff lambda, and IR cutoff L. Put our theory in a box to get a finite answer. But our final answer didn't depend on either cutoff. It didn't depend on L. It didn't depend on lambda. It is independent. This is a general feature. In physics, we expect that we can do a measurement at one energy scale without having to care about much larger or much smaller energy scales. In quantum field theory, we sometimes need to think explicitly about what's going on at much larger or much smaller energies, and account for that in our calculations. But in the end, our final result won't couple different energy scales together. So there's a number of objections you could raise to this derivation. One is, why did I use these particular regulators? Particularly this one. This is a very crude model for what's going on when the field is interacting with the plates. It's not very realistic. There's no field we know that would have a sharp like step function dependence on how it interacts with the plate. More realistic thing might be some sort of smooth transition where the low energy modes are interacting strongly with the plates, high energy modes are interacting weakly. What you're going to show in tutorial this afternoon is, in fact, it doesn't really matter what cutoff you use, what model for the cutoff. This result is physical, finite, doesn't depend on what's going on at much higher or much lower energies, as long as we do account for the physics of the problem. My apologies for going a bit over time. Started a few minutes late, but thank you. Yes.
Is there a physical way to understand why our result doesn't depend on L?
On L? Yeah. So this is the L goes to infinity limit as well. There'll be corrections to this that are like kind of wrong. Yes.
Energy as A plus.
So the field in this region, there'll be some set of modes that are allowed in this region. There'll be a mode with no nodes or one node. And so if we want to find the energy associated with this region, we add up all the modes that are allowed in this region. And the same thing over here.
We have like 3 plates, 2 of them are 6, and the one in between is like
this is plate 1 over here. Space is periodic, so this is the same plate. We have two plates. We're imagining we're fixing one of the plates and allowing the other one to move around. Yes.
We were assuming a massless field?
Yes. Basically, because we're using this. The final result doesn't depend much on that, but some steps in the derivation do.
If the space is periodic.
Sorry.
No, my question wasn't about periodicity. This is.
Oh. If the space is periodic, then the regular doesn't make physical sense because even for wave modes which go beyond the plates, they're still in the plates. Like that interact with the
If they don't interact with the plates, then they have no A dependence, so they won't contribute to the force.
Basically, the result that we got is like if in that divergent result we plug like Ramanujan's solution to that series, the -1/12.
Yes.
What we are getting.
Yes.
We could have done that without taking L to infinity. Why that doesn't work?
We'd have an extra term here.
I mean, if we do that and take L to infinity, we get exactly that.
Yes.
Why should we take L to infinity?
We might be interested in this setup in Minkowski space instead of hard to set up periodic space in the laboratory. So theoretically, this is an easier setup, but experimentally with oligo to infinity is.
Then you just have the plates outside and they just smell. So it's easier to understand.
In L goes to infinity, this copy of plate 1 goes to infinity, and you're just dealing with the plates. Because, well, physically, there's no experiment we can set up that will impose this condition exactly for all modes. This can be a good approximation, but it will break down for sufficiently large n. Taking into account some of the capabilities of experiments is essential for getting finite and physical answers in quantum field theory. There's many examples of different things that seem like in principle they could be measured, but if you think carefully about experiments, experiments will always have some limitations, and those limitations are taking into those limitations into account is essential for getting a finite answer. Yes?
But when?
Yeah.
I'm wondering if we could somehow get this result from there by maybe taking the normalization of that series to be like the zeta function of -1, where it becomes -12.
You're going to do that in the tutorial, yes. Yes.
I think that's possible. Can I ask something?
Of course.
It feels like every time we get the divergence in our equations, it's like we're trying to destroy Heisenberg's uncertainty. Like there, we wrote like delta 0.
That's right.
It's like knowing the position. So,
yes.
And here, when we got to infinity, was like probing very small frequencies, which is like knowing the velocity.
Yes.
So yeah.
That's a very insightful observation. Thank you for sharing that.
Okay. Is there a way to like? So this is a way to think of when I will anticipate to get infinities.
Mm-hmm.
Okay. So.
I think that's a very useful way to think about it.
This is why when we get loop diagrams, is this the same reason that we get like infinities that we cannot get rid of. Like it's like we're constantly trying to probe very small distances in our theory.
Yes, in a sense, loop diagrams are probing arbitrarily short distances in theory, so you need to account for the fact that it doesn't quite work that way.
Is there a way to think why we cannot renormalize some theories with that point of view?
So non-renormalizable theory is, in my opinion, something of a misnomer. What non-renormalizable really means is that if you want to make predictions with infinite accuracy, you need infinitely many inputs. You need to specify the result of infinitely many theories. That again, that's not a really reasonable thing to demand of a theory if you're thinking about real physical experiments that always have some intrinsic limitations of how well they can measure things. So really what we need is a theory that can make predictions with some small but finite accuracy. If you demand that your theory make predictions with small but finite accuracy, then you can renormalize a non-renormalizable theory using a finite number of inputs.
Okay.
So,
but is that setting a cutoff in a distance or a momentum? Like impose it, not test.
There are many ways you can impose the cutoff, and sometimes there's technical reasons to favor one over another, but for understanding the physics, it really doesn't matter.
My question was if I demand to have a finite input, that means that I have to choose somewhere to impose a cutoff, right?
No. So your physical theories will have a finite number of parameters, and you can specify those parameters by saying that the result of an experiment with these inputs and or this initial state and that final state is related to one of our parameters in a particular way. And so you can, that's what I mean by when I say inputs to the theory.
I confused parameters with coordinates or like, yes.
Okay. No, so I meant by parameters, I'm talking about things like masses of particles or coupling constants that determine the strength of interactions with different particles.
And you said something about that or I understood that in classical physics we think that we don't need energies much higher or much lower from what we are measuring to understand that. I understand when we put a high energy cutoff, we are trying to, like when we normalize, we are trying to understand how those high energy degrees of freedom are important in this energy explanation. But does it happen the other way, that we need to use information of a lower energy to get this energy description? What would that mean?
That's certainly less common in quantum field theory, at least if you're dealing with massive theories where all the particles have mass. Yes. IR divergences like the one we encountered here basically don't occur in at least non-gravitational theories with massive particles. If you add gravity or you make things massless, then yes, sometimes you do have to worry about that. Basically, because the mass provides a cutoff for your theory. You have a gap between your ground states and your one particle state, so there's nothing interesting happening in a region near your lowest energy.
Doesn't normal ordering interfere with the transformation property of the Hamiltonian? Does it should still transform as a vector as part of the Poincare representation?
No, it doesn't affect that.
We should normalize the momentum part.
Sorry, can you repeat that?
Is a vector component. The energy and
Yeah.
the free part is the
Yes.
We should still transform the same way under Lorentz transformations.
Right.
We just modify the Hamiltonian, one of the components. The subtle Lorentz invariant modification.
But we're doing, in a sense, not a very interesting transform change to it. We're just shifting it by constant.
Can we do that? Relativistic theories, like the energy is fixed. In classical theory, we can shift the energies, but in relativistic theories, we don't.
In special relativity, you're always measuring energies relative to some ground state. There's a natural zero. I mean, you want to define, often want to define things so that particle has zero momentum, zero energy, or energy of m squared.
Then if you modify the Hamiltonian, then the length will change.
Right.
Which is related to the mass.
Oh, I see what you're saying.
Or does normal ordering change the Hamiltonian and the momentum part in such a way that the length of the vector?
So we're normal ordering all of our operators, including momentum. So that yeah, it should. Yeah, I haven't thought about that. If you tried to normal order one operator but not another, it might cause some problems. But should be fine. Yes.